Assalamualaikum. Let's start lecture number 40 and we will discuss the topics on related to chapter 7 in which we study general state of stress and transformation of stress in 3D and also Mohr circle in 3D. Okay, let's see. Lecture we will discuss general state of stress and three-dimension analysis of stress and we will only look at the general state of stress and we will see what is the Mohr circle in three dimension and we will apply that concept to the plane stress. Means we will apply the concept of uh, Mohr circle for 3D case Mohr circle to our plane stress. Why we are doing that we will see. Okay, so we will apply this concept of 3D Mohr circle to plane stress. And first we have to see what is the general state of stress um, and then three-dimensional analysis of stress. Next lecture will be on the stresses in thin wall pressure vessel. We will discuss in the next lecture. Okay. Now let's consider a element uh, which have a 3D state of stress in which we have non-zero stresses of sigma x, sigma y, sigma z. So we have all six component stress on that point, single point Q, and we are taking a tetrahedron on that element. Means this face AQB that has sigma z, tau yz, and tau azx. The face BQC, this face, will have sigma x, tau xy, and tau zx, and the lower face, that is AQC, that face will have stresses of sigma y, tau xy, and tau yc. Okay. Now, if you remember that for the case of plane stress we have what? In plane stress, sigma z, tau yz, and tau zx will be 0. But over here we are talking about general state of stress. Okay, at point Q, and these are the area. Let's take this area lambda y dA, lambda x dA, and lambda a dA. Basically, lambda is direction cosine for this normal vector on the area ABC. So we are interested what will the stresses along that normal and we have a direction cosine with lambda 1 is basically cos, I can write cos theta x, means what is the angle between this normal and x-axis, and sorry, lambda x, lambda y is cos theta y, angle between this normal and the y-axis, and lambda z is equal to cos theta z, that is angle between this normal and z-axis, cos of that angle. So these are basically direction cosine we have, lambda x, lambda y, and lambda z. And we are interested what is the stress along that normal n. So by considering that sum of forces at normal direction should be equal to 0, so we convert into forces that multiplying with the area and delta A will cancel out and we put the value, so this becomes sigma n is equal to sigma x uh, lambda x square plus sigma y lambda y square sigma z lambda z square, and similarly 2 times tau xy lambda x lambda y, 2 times lambda yz lambda y lambda z, and 2 times lambda zx lambda z and lambda x. In detail we will discuss in next course, that is mechanics of solid 2. So over there we will discuss about 3D transformation stress for the general case or 3D case, and over there it will become more clear. But over here, in this course we are just getting an idea for 3D state of stress, and we will apply to our 2D case. Now, let's suppose these stresses that sigma x, sigma y, and sigma z are principal stresses. Means, what is the definition of principal stresses? At principal stresses, your shear stress will become 0. So this equation will reduce to sigma a, lambda a square, sigma b, lambda b square, and sigma c, lambda c square, where sigma a, b, c are my principal stresses. And lambda a, lambda b, and lambda c is the direction cosine with respect to my principal planes to that normal. Over here, sigma a, sigma b, and sigma c are my principal stresses. Now we have how many? Three principal stresses. Previously, in case of plane stress, we are considering two principal stresses, and third one was 0 because third state of stress was 0. And if I rotate this coordinate, okay, now this time the rotation will be at origin, not with respect to z-axis. In this case, it will be with respect to this origin. So if at certain orientation for general state of stress, the shear stress will vanish and you will left with normal stresses. And these stresses will be your principal stresses. Over here you will have a maximum stress, and you have a minimum stress, and you have a stress in between maximum and minimum, where at that orientation the shear stress will become 0. Okay, so in general state of stress you have three principal stresses, but in case of plane stress, you have sigma max, sigma minimum, whereas the sigma c, that third stress you take, that will be a 0. Now, when it will become significant, we will see. Okay. Now, if I want to draw more circle, let's suppose if I have state of stress given, so transformation stress, I can rotate to some orientation that will be, we have Mohr and principal axis, and if I draw Mohr circle for that, so that it have a circle. Now we have three circles. Now first circle, that means C1 will be between sigma A and sigma B. These are my principal stresses. Now circle 2 will be between, let's take sigma B and sigma C. And the third circle is between sigma A and sigma C. Now, how we are arranging that? Sigma A will be greater than sigma B, and sigma B will be greater than sigma C. Means the maximum stress will be my sigma A, and sigma minimum will be sigma C in this case. Now, in previously, we were drawing 2D Mohr circle, right? And we have circle like this. But the third principal stress was 0. Now, if we consider that if let's suppose sigma c is, now we have maximum shear stress between the radius of A and B, right? There can be a maximum shear stress that is between sigma c and sigma B, that is radius of this circle, and there will be a maximum stress between A and C, and that will be the overall maximum shear stress in the system. Okay, now we are interested what will the maximum shear stress, because if you remember that ductile material, they are weak in shear. That's why, and sometimes you need a value of shear stress, maximum shear stress at certain location. So in order to find the shear stresses, so you have to consider those values. Now, three circles represent normal and shearing stress of rotation each principal axis. Means if I want to find what is the shear stress, maximum shear stress between this circle AB, so I have to rotate about C axis. Now if I have to find the stress between B, C, then I have to rotate about A axis, and uh, if I want to find the maximum shear stress between A and C, then I have to rotate the element about B axis. Means the maximum shear stress in this case will be present. Let's suppose if I'm interested in the maximum shear stress between sigma A and sigma C, then I have to find, if I rotate this element 45 degree with respect and taking the axis of rotation B, then at that orientation I will have a maximum shear stress tau max, and that will be equal to radius of the circle AC. Okay, now radius of the largest circle, in this case tau max, is what? Tau max will be 1 over 2 sigma max by minus sigma minimum. So this is the case of 3D case. And how to use this 3D case for our plane stress problem, because in this course we are only restricted to the plane stress, that is the 2D case. Okay, now let's see. Now in case of plane stress, now the maximum and minimum stresses, those are the principal stress. Let's suppose we have a state of stress sigma x given, sigma y, and sigma tau xy is given on any point, whereas sigma z, sigma tau, let me correct this one, tau xz and tau yz is equal to 0. So this is my plane stress state, right? Now in this case we know that we have sigma max, and that we can find sigma average plus radius, and we have sigma minimum, that we can find sigma average minus radius. And okay, now if the case is like that, the sigma max is greater than 0 and sigma minimum is less than 0. What does it mean? Means that the maximum normal stress, the principal stress, is tensile in nature, and the minimum principal stress is compressive in nature. Then we have a circle AB. So in that case we have a circle AB. So AB circle we can draw. But the third principal stress, sigma C, is always 0 because it's a case of plane stress that is related to my z-axis. Okay. Now if I draw Mohr circle for 2D case, that will be the solid circle. But there must be another circle between A and 0, B and 0, right? So this will give me the complete picture of the state of stress at even we have a plane stress case. Okay, the principal axis now that now if I look at A and B representing the principal planes are on opposite side of the origin, then the corresponding principal stress are maximum and the normal stress for the element and minimum normal stress for the element. And the maximum shearing stress in this case equal to maximum in-plane shearing stress. If you remember that previous some problem we discussed that in-plane shearing stress. So in this case, so what does that mean? It means that suppose we have sigma A, we have sigma B. Now sigma A is tensile, sigma B is compressive, whereas sigma C, that is along z-axis, will be 0. So along this, sigma Z is equal to 0. Now the maximum shear stress will be between the plane. If I rotate this plane between A axis and B axis, those are my principal axis, If I rotate it 45 degree, then I will have maximum shear stress, and that shear stress is known as in plane shear stress. Means if this is my element and this is my A axis, principal axis, this is my B principal axis, and that is my third one, C, that is equal to Z, because we are rotating about Z for plane stress case. So the maximum shear stress will occur if I rotate this plane 45 degree with respect to my Z axis. So Z axis will be the axis of rotation, but if I rotate this, if I take a plane at 45 degree, this angle will be 45, this angle will be 45, but you can say rotating about the axis in between. So on that plane, the shear stress will be tau max, absolute maximum shear stress on the system. Okay. Now, if we consider now the second possible case, again, the second possible case for the plane stress is if I'm talking about plane stress, that sigma z, tau xz, and tau yz is equal to 0, and we have non-zero state of stress, and we know that the maximum stress is equal to sigma average plus radius, and principal stresses, and sigma minimum is average plus minus radius. Now in this case, let's suppose sigma max is greater than sigma minimum, and that is also greater than 0, means the maximum and minimum principal stresses are tensile in nature. Then if you draw the circle, this corresponding circle will be this solid circle, but the third principal stress is 0, so sigma c is minus 0 because it's a plane stress case. Now what? So there must be a circle between B sigma minimum and 0 and sigma maximum and 0. Now if you draw a circle, you need two more circles to complete the picture. So there will be a circle between B and O, and then there will be a circle between A and 0. O. Now if you look at the what will be the maximum radius of the system or the Mohr circle, that is tau max will be 1 by 2 times sigma A. So if you remember that, now in this case the absolute minimum stress is what? 0. So if you remember that in 3D case, tau max is equal to 1 over 2 sigma max minus sigma minimum. Now sigma max is, you know that from that formula, but sigma minimum, absolute minimum is 0. So that why the maximum shear stress is between A axis, principal axis, and Z axis, or if you take plane 45 degree to the A axis or Z axis. So the maximum shearing stress of the element equal to half of the maximum stress, because the minimum is 0 in this case. The plane stress or the shearing stress are 45 degree to the plane, and this is known as out of plane shear stress. Means if I again draw the element, just to clarify, so this is my A axis principal axis, this is my B principal axis, and this will be my Z is in principal axis, because we are rotating about Z. It's a case of plane stress. Now the maximum shear stress will be if I rotate this plane, any of the face, this face or this face or this face or this face 45 degree. So on this face, if I take this face, the shear stress acting parallel to this red face, that is my absolute maximum shear stress. and that is known as out of plane shear stress. Out of plane shear stress. And now, depending on the nature of principal stresses for plane stress case, your maximum shear stress can be in plane or out of plane depending on the nature of stresses. Now, the maximum out of plane shear stress can also occur if sigma A and sigma B both are less than 0, means sigma A, these are my principal stresses, and whereas sigma C is equal to 0. Now both are compressive in nature. Now if I draw Mohr circle for this case, so let's suppose this is my sigma A, this is my sigma B, right? Now again this is one circle, but in order to have complete picture, I have one circle between sigma B and 0 and the third circle between sigma A and 0. Now the maximum shear stress will be radius of this outer circle between sigma A and 0. Now in this case, your tau max will be what? The formula, if you remember the formula, that is 1 over 2 sigma max minus sigma minimum divided by 2. Now in this case, if I write 1 over 2 sigma max minus sigma minimum divided by 2. Now in this case, the sigma minimum is equal to my sigma A. And what is sigma max? Absolute max is equal to 0. So in this case, when the both principal stresses are compressive, so shear stress again, it will be out of plane, and that will be equal to 1 over 2 times sigma A, the absolute value fatigue. Okay. Now, depending on the nature of stresses, if you have both tensile or both compressive principal stresses for plane stress case, your maximum shear stress will be out of plane. But if one of the principal stress is tensile and other is compressive, then the maximum, the absolute maximum shear stress on the system will be in plane. Now, let's suppose you have to design something. It's a ductile material, so, and you have a plane stress state. But if you take in plane shear stress, then in that case, the system will fail, and because you have calculated with respect to in plane, but the maximum is out of plane. So you have to be careful by calculating during the calculation of those stresses. The concept problem number 7.3 for the state of plane stress shown in figure 7 over here. So we have to find the maximum three principal planes and the principal stresses and the maximum shearing stress. So depending on the nature of principal stresses, we have to find what will the maximum shearing stress. Okay, now first we have to find principal planes and principal stresses. So we know that principal planes we can find tan 2 theta p 2 times tau xy divided by sigma x minus sigma y. Now in this problem, the sigma x is 6 kilopound square inch KSI, and we have sigma y is 3.5 KSI, and tau xy is minus 3 KSI because of this direction. Okay, now putting the value 2 times minus 3 divided by 6 minus 3.5, and when we solve it, so this tan 2 theta p or 2 theta p, p is approximately 67.4 degree minus 67.4 degree, and theta p is 33.7 degree. Means if I rotate this element with respect to z-axis 33.7 degree like this, so this, if I rotate this element with respect to z-axis 33.7 degree, over there we have a principal stresses. Now What are the principal stresses? Sigma, let me write sigma A and sigma B because it's a state of plane stress. So sigma C, so let me take sigma C will equal to 0. The third principal stress will always equal to 0. Okay. Now sigma A and B, those are my principal stresses. I can write sigma average plus minus radius. What is sigma average? Sigma average is sigma x plus sigma y divided by 2 plus minus under root sigma x minus sigma y divided by 2 square plus tau xy square. So putting the value, so we have 6 plus 3.5 in KSI divided by 2 plus minus under root 6 minus 3.5 divided by 2 square plus minus 3 square. Now if I put the value and if I solve it, so sigma A, that will be equal to 8 KSI and sigma B is equal to 1.5 KSI, and obviously sigma C will be equal to 0. Now two principal stresses are tensile in nature and third is 0 because it's a case of plane stress. Now if I draw Mohr circle, that is A, part A. Now what will the maximum shearing stress? So it will be in plane or out of plane. So let's see. Now I know the principal stresses. What are my principal stresses? So sigma A was 8 KSI. Sigma B was both are tensile in nature, 1.5 KSI. And sigma C is 0. So if I draw Mohr circle, that was sigma A, this is my sigma B, those are my principal stresses. It will be something like that. Again, this is a little bit out of scale. And third principal stress is 0. Now if I draw the third circle, so second circle, so it must be between this sigma B and 0. And the third one is the largest circle will be between 0 and sigma C or 0 and sigma A. Now the maximum stress is this radius of this circle, tau max. That is my out of plane shear stress. And we know that out of plane shear stress tau max is half of, we can write sigma max minus sigma minimum. So sigma minimum is 0 in this case. So and tau max is 1 over 2 sigma A. And if you put the value 1 over 2 multiplied by 8 KSI, so tau max is 4 KSI. But if we consider that, if we don't consider that what will be the absolute maximum shear stress, then if we take the radius, the tau max is equal to radius of the original Mohr circle, this one, so then it will be 3.25 KSI. Now if you are designing something and you calculate it using this value, then your system will fail. Obviously the maximum shear stress is actually 4 KSI as compared to when you're considering 3.25 KSI. Okay, so you have to be careful when you are calculating the value of maximum shear stress. Okay, so let's see another problem related to this topic. Okay, let's see problem 7.76, and the given is for the state of stress shown, determine the value of sigma y for which the maximum shearing stress is 73 megapascal. So the given is the maximum shearing stress is given, tau max. So tau max is given, that is 73 megapascal. and the state of stress is given that we have sigma x is minus 50 megapascal, tau xy is 48 megapascal, and the shear and the sigma y we have to find, that is unknown. Okay. Now, this tau max is not mentioned that is in plane or out of plane. So the maximum shear stress can be in plane or out of plane. So we will have two cases. So case one, when we take tau max as maximum in plane shear stress. Means it will be equal to the radius of the equation. And case 2, and also for the case 1, that sigma maximum will be tensile and sigma minimum will be compressive, and whereas sigma c, the third principal stress, will be 0. Okay. Now case 2, when tau max is maximum out of plane shear stress. So in this case, sigma max and sigma mini or sigma b both will be greater than 0, and sigma c will be sigma minimum, and that will be equal to 0. So third principal stress will be 0. Okay, now let's start with the case 1. So in which the tau max we said in maximum in plane, and that will be equal to radius equation, or sigma x minus sigma y divided by 2 square plus tau xy square under root. Okay, now let's put the value and find what we get from here. Okay, let's put the value. So we know that tau max is 73 megapascal, and sigma x we know that it's minus 50 megapascal. Sigma y we have to find, divide by 2 square plus 48 square. So when we take a square on both sides and expand it, so we come up with this equation: sigma y square plus 100 times sigma y minus 9600 is equal to 0. Now this equation will have two roots, and if we solve it, so sigma y we have two value. First will be 1 minus 160 megapascal, and the other value is 60 megapascal. Now we have two value. Now we have to check that which value is valid value. How we will check? We will find the maximum and minimum principal stresses or normal stresses, and it must satisfy the condition that sigma max must be tensile and sigma minimum must be compressive, whereas sigma c will be 0. So this condition must be satisfied. So we have two stresses, and we can calculate those stresses. Okay, let's see. Let's take both the value, and first we will have to check the validity of both the value. So let's take as first sigma y is equal to minus 160 megapascal. So it's must satisfy the condition of Mohr circle. Now the Mohr circle, we are looking for that one value of sigma A should be positive, sigma B should be negative, and obviously the sigma C is 0. So basically in plane shear stress where we have sigma A and sigma B will be non-zero, but one will be compressive and other will be tensile, where sigma C is 0. So this is the condition we have to check, validity of this condition, and let's see, for sigma y is equal to minus 160 megapascal. So we have to check what is the value of sigma A and sigma B. So sigma A must be greater than 0, it should be tensile, and sigma B must be compressive. So if we put sigma average plus radius, now we don't have to calculate the radius because we already know that that is 73 megapascal. So we have sigma x plus sigma y divided by 2 plus radius. So sigma x is minus 50, sigma y is, we calculated, minus 160 divided by 2 plus radius. And if we put the value, so this will become sigma average is minus 105 plus 73, and that will become minus 32 megapascal, now which is compressive in nature. So sigma B is sigma average minus radius, and if you put minus 105 minus 73, so this will become minus 178 megapascal, and sigma C is 0. Now if you look this, if I draw more circle for that condition, so we have sigma A, sigma B over here, sigma A, and obviously sigma C is 0. So if your circle will be between A and B, this is in plane shear stress top. But that is not valid because the maximum shear stress is out of plane shear stress between sigma B and sigma C. So this value of sigma y is equal to minus x is not a valid value. So this value of sigma y is equal to minus 160 megapascal of 160 megapascal is not valid because it is giving the maximum shear stress out of plane shear stress. So we are not consider the value we get from the maximum in plane shear stress. Now let's see the other value, that sigma y is 60 megapascal. How about that? Let's check this value. So this will be sigma A will be sigma average plus radius, and we know that sigma average is sigma x plus sigma y divided by 2 plus radius. And let's put the value. So minus 50 plus 60 divided by 2 plus 73. So this will become 5 plus 73, and that is equal to sigma A is 78 megapascal, which is tensile in nature. Now if we put sigma B, that is sigma average minus radius. So 5 minus 73, so it becomes 68 negative 68 megapascal. Now it is satisfying the conditions because sigma C is 0, sigma A is greater than 0, sigma B is less than 0, compressive in nature, and sigma C we already know that is equal to 0. Means the Mohr circle, if you draw, it will be like this. So the value of sigma y is equal to 60 megapascal is valid value. It's a valid value. So now if you're taking maximum shear stress in plane,
then sigma y must be 60 megapascal. It cannot exceed 60 megapascal. Okay. Now, the second case, when we are talking about out of plane shear stress. Now, case 2, let's take case 2. Case 2, we are saying that we are talking about out of plane shear stress. Case 2. It will be relatively simple. So, case 2 will be tau max we are taking out of plane. In out of plane, tau max we can write 1 over 2 from previous lecture, sigma max minus sigma minimum. Okay, and we know that tau max is 73 megapascal, 1 over 2 sigma max, because for out of plane shear stress, sigma A will be tensile and that will become sigma max. Sigma B will be again tensile and sigma C will be 0. So non-zero will be maximum will be sigma A. So we can find the sigma max, very simple. So sigma max will be 2 times 73 megapascal and it will be 146 megapascal. Because sigma max is equal to sigma A and sigma minimum will be equal to G sigma C, that is equal to 0. Now, maximum for plane stress case, we know that equal to sigma average plus radius. Now, in this case, the radius cannot be 73 megapascal because we are talking about out of plane shear stress, where the maximum one is 73 megapascal. So we know that this is 146. Sigma average is sigma x plus sigma y divided by 2 plus under root sigma x minus sigma y divided by 2 square plus tau xy square. Now, I can write this as 148 is equal to minus 50 plus sigma y, we don't know the value because we are calculating, divided by 2 plus minus 50 minus sigma y divided by 2 square plus tau xy square, and this value is under. Okay, now I can rearrange 148 plus 50 minus sigma y divided by 2 is equal to, I can take negative sign out, 50 plus sigma y divided by 2 whole square under root plus 48 square. Now, multiply with this whole equation with 2, so that will become 292 plus 50 minus sigma y 2 times is equal to under root 50 plus sigma y divided by 2 whole square plus 48 square. Now, if I take both sides, square, or okay, let me further simplify, this will become 342 minus sigma y is equal to 2 times under root 50 minus sigma plus sigma y divided by 2 square plus 48. So let me take a square on both sides and expand. So when I expand it and when simplify it, so this value will become So you can also check, maybe hopefully I'm doing it right. 116964 minus 684 times sigma y plus sigma y square, and that will be equal to 2500 minus plus 100 times sigma y plus sigma y square plus 9216. So sigma y square will cancel, and we will left with the minus 784 times sigma y is equal to minus 105248, and sigma y is equal to, if we solve it, 134.24 megapascal. And this is a valid value uh, because the both will be a tensile stresses, and if you put the value, so the sigma b will also greater than 0. You can check. So again, this will be a valid value or okay value, considering that out of plane shear stress means if I draw Mohr circle for this case, it will be sigma a over here sigma b, and sigma c will be 0. And we have a one circle between a and b, and there will be another circle between that will be another circle between, let me change the color, B and C, and the third will be between sigma C, that is 0, and sigma A. And we are taking that maximum shear stress is this one out of plane, and that was equal to 73 megapascal. So when you're designing, if you consider maximum out of plane shear stress, so your sigma y should not be exceeding 134.24. But if you're designing for in-plane shear stress, means the maximum shear stress will be in plane, then it must not exceed 60 megapascal. Okay. Now, these are some assignment problem related to section 7.4. So you have 5 problems. To clear the concept, it will always clear your concept regarding the maximum in plane and out of plane shear stress. And you can see the significance. Even this third principal stress or third in case of plane stress 0, but it also contribute for the maximum shear stress value. Okay, thank you very much.